continue the session on the pilots. We finished with 2 pilots in Storm. We still have a full-scale pilot in Jordan, in Ajloun, that will be presented now. And then after, we will have a presentation from Barcelona, from our colleagues at KIM-BCN and their associate partner, District NEMA. So we'll start with our partners in Jordan, Royal Scientific Society, and we have Hussam Manasir, and we have Ahmed Zaid. So Hussam, the floor is yours. Go ahead.
Hello, everyone. Our partner talked earlier about 2 presentations about university campuses, but I want to take you like something different. Here is Ajloun Forest Reserve. It's located in northern Jordan. It's about 1,200 meters above the sea level. It's a biosphere, a UNESCO biosphere reserve, also one of the top 100 sustainable destinations over Jordan, over the world, sorry. Before we talk about overview about the problem of the bungalows and how our pilots are implemented to solve this problem, I want to say like overview about me. My name is Hussam Al-Manasir. I'm from Royal Scientific Society, specifically from National Energy Research Center. Our role is to do an energy research in energy efficiency, renewable energy, and a new implementation, a new technology implementation. We are a partner project in Storm. Also, we are our associate partner, RSCN, also are with us for implementing this project. They are responsible for the Ajloun Reserve Forest, and they are also responsible for 9 others reserve across Jordan. Okay, let's talk about a little bit about Ajloun Forest Reserve. It's far away, about 80 kilometers from the capital of Jordan. Also, it's about 13 kilometers of Mediterranean oak, pine, and curve forest. Also, it's contained about 38 eco-cabins in open year-round. Let's take some numbers. During 2025, they have welcomed 7,300 visitors during 2025. Let's like distribute this in like occupancy rate. As you can see, in July it's about 65.5 occupancy, but in December it's only 11.4. So we can take like indicator of that reserve it's only work in summer, and in winter it's barely like empty. So why is that? Because in winter the cost of heating the reserve it's quietly high price. So when the price of heating demand it's increasing, also the booking will be increased. That's why there is not a lot of visitors during winter. So this is a photo of the location of the reserve, and this is the bungalows that we are looking to implement our pilot. I guess it's the right place to insulate from the world here, because I would say it's adapt to the nature. Let's say about the problems. Unfortunately, the heating required in the bungalow, it's connected to the Jordan electricity grid, and the Jordan electricity grid is 90% fossil fuels based in natural gas and heavy fuel oil. Regarding to the thermal demand, about 80 megawatt hour per year are required for the bungalows itself, 60 megawatt hour for heating demand, and 20 mega hours for domestic hot water. And they paid about 57,000 euro only for heating the bungalows during winter. And unfortunately, they are not using any renewable for heating or using for domestic hot water. So why this pilot matter? How can it change this scenario? If we use a seasonal storage tank, we can save about 33 tons of CO2. Also changing the electricity to the solar energy. By that, if we demonstrate that the pilot are successful, we can replicable these things to other 9 reserves that RESCN are responsible for across Jordan. Also, it's can considered as a blueprint for Mediterranean's natural resources. We talk about environmental. Now we want to talk about the tourism itself. It can change the occupancy rate from 7.2 to 20%. So because the bungalows are rely on split units, they use electricity. So if we use a solar energy thermal storage, we can reduce the cost of electricity. Then the cost of booking will be lesser, and the visitor will increase about more than 436 guests. Also, the other things that we can benefit, it's the local women's enterprise. There is a local women enterprise beside the reserves. They are working in soup houses, biscuits houses, and other things. So if we make the bungalows also work in winter, they can work also over the whole year. Also, I want to mention something that we are working to the pilot. We are not working only for the technical and the financial. We are like focusing also to the ecotourism things, because we cannot implement anything if we affect the nature of the place. As you can see, the bungalows are fit to the nature. Because there's another reserves also depends on the nature, if it's desert, if it's trees, etc. So it's the concept is very simple. It's taking the sun, use it for charging the seasonal storage tank by the solar thermal energy, then discharge it in winter for the bungalows. And Ahmed will take the lead for the technical aspects and tell you more details about it.
Hello, everyone, and good morning, still morning. Thank you for being here today. My name is Ahmed Zayed, and I'm a senior energy specialist at Royal Scientific Society. And I'm also leading the work related to the design and implementing pilot in the Jordan. As Hussam explained earlier, the story started from how we can provide these eco cabins or bungalows within heating and domestic hot water system with a more sustainable way. So today I will walk you through the story of this pilot, where we started, what we measured, and how the Transys model was developed, and how the next phases will move us from simulation toward implementation. So the main objective of this pilot is to design and simulate and demonstrate solar thermal energy storage for the bungalows in Ajloun National Reserve. The system is intended to provide a renewable heating and domestic hot water using 4 main elements, as you can see. First one is the solar thermal collector, which acts as the main renewable heat sources. The second one is the thermal energy storage tank, which store the heat and help balance supply and demand. The third one is the heat pump, which works as a backup and supportive when a solar energy is not available. And finally, the transit simulations, which allows us to use allows us to size and optimize the system based on the actual performance data. Okay, let us look at the overall system concept. The concept of the system is quite simple. So the solar thermal collector capture heat from the sun. Then the heat is transferred to the thermal storage tank. When there is a heating or hot water demand from the bungalow, the system uses the stored heat first. Then if the storage temperature is not enough, the heat pump operates as an auxiliary source. But before designing any system, we had to understand the site itself. The bungalows are distributed across the area. This creates a technical challenge. To be honest, this is a critical technical challenge because a longer piping network may increase heat losses. And if we are not designing properly the site, at the same time, we had a heat loss more than we calculated. So any intervention must respect the landscape and the environmental context. Currently, split AC units are commonly used, which contributes to electrical demand. Before developing the system design, we needed to know the real measurement behavior of the bungalows. So if we use, as the rule says, if we use a generic value, then we get a generic result. But if we use a measured data from the actual site, the model becomes much representative. So let us look at the field approaches and instruments used during this stage. During the site work, sensors were installed at different measurement points to record indoor and outdoor temperature. We also conducted a U value and envelope measurements to understand the actual thermal performance of the walls, roofs, floors, and glazing also. More than 148 hours of continuous logging. In addition to temperature logging, we also use a thermal imaging to better understanding the heat loss areas. Thermal imaging was used to identify the surface temperature variation and heat loss areas. So we had two types of information we working together. The first one is the thermal image, and the second one log data showing how temperature changing over the time. The next step was to analyze the indoor thermal conditions. This is important because heating demands is not constant. It is changed depending on the outdoor temperature and the building envelope and the time of the day and the internal conditions also. In simple terms, this data helps us to answer two questions. How strong in this demand, in the demand, and how does this demand change over the time or over the day? So, but the temperature also, the temperature data alone is not enough. We also needed to assess the building envelope itself. So the bungalows are based on a timber frame construction as a construction type. Window aisles and sliding balcony doors can contribute significantly to heat loss, especially during cold period. And the thermal bridges also identified and mapped. All of this information was translated into the Transys model input. In parallel with the thermal measurements, we also looked at the existing electrical operational conditions. As you can see here, the goal was to understand the existing demand profile and document the current operation conditions. After collecting these data, it was proceed and prepared a Transys ready inputs files. Now let us see how the field measurements were transformed into Transys input. All the information collected from the site was translated into the Transys model: surface, wall, surface temperature, wall and roof U value, and we had a zone definition. So this allows the Transys model to calculate the heating demand by zone and domestic hot water demand profile, and finally the seasonal energy variations. Okay. To represent this reality inside the simulation environment, I mean the Transys model, we also need a geometric model. So in this stage, the real bungalows was translated into a simplified SketchUp geometry. The goal was to capture the thermal elements that matters most, like a shape, orientation, area, zoning, and spacing, and so on. So the process moves from the real bungalows to SketchUp geometry, then to the Transys model as a simulation environment. After preparing the geometry, the next step was to develop the thermal building model. This slide shows the main steps used to develop the Transys building model. First, the site geometry was defined, as you can see. The second one, the envelope parameters was applied using the measured U value. Third, the thermal zone were defined also. And fourth, the simulated temperature profiles can be compared with the measured data to check whether the models behaves realistically. Okay. Once the building model is ready, we can start building the full system model around it. So as you can see, the Transys model, we have the weather data for Ajloun is used to represent solar radiation and ambient temperature, the building thermal zone by zone heating demand calculations, and the solar collector loop models, the evacuated tube collectors, the thermal storage tank as a buffer tank charge discharge cycle. Also, we have a heat pump as a backup and supportive. The last one, the control logic defines how the system operates. Through this model, we can generate outputs that will guide the final design. In this slide, you can see the annual heating demand profile that shows annual sensible heating load profile for bungalows. As you can see here, the simulation time for 8,760 hours along the years, and showing the seasonal demand variation and peak load periods. Also, in this slide, this slide shows the tank thermal energy storage tank performance. It helps us to define the collectors, storage volume, heat pump capacity, and operating strategy. Based on this, we can now look at the proposed system component. This slide shows the main component of our proposed system. The solar thermal collectors capture the heat from the sun by evacuated tube primary source. Then it transferred to the heat exchanger from collector loop to the water or storage loop. The tank thermal energy storage tanks acts as a buffer and a thermal storage element. The heat pump provides backup heating when needed, and then the domestic hot water cylinder supplies domestic hot water. Finally, the heat is delivered to the bungalow through fan coils. So after understanding the technical system, we need to translate it into the physical layout on site. I think this part of the presentation moves us from simulation to real implementation thinking. As you can see, I prepared a simplified site layout as shown in the figure. The system components are distributed around the targeted bungalows. Here's our target bungalows, and here is the land we will put our components here, including the solar collector field, the planet room, and the underground thermal storage tank, the air source heat pump, and the distribution pipe routes connecting system to the bungalows from 1 to 5 as a pilot project. So the purpose of this layout is not to show the final detailed design, but to visualize how the system can be practically integrated on site. It also helps us to identify important implementation issues, such as a distance, pipe routing, excavation work, accessibility for maintenance, heat losses, cost, and visual impact. Let us start with the most visible part of this of the system, the solar collector. We need to identify a location with a good solar access. The collector should have a suitable orientation, preferably toward the south, and tilt angle optimized for the heating season. We also need an area with a minimal shading. That's why we select this land, especially from trees or a surrounding landscape elements. At the same time, the location should be compatible with the protected reserve settings. This means we must consider visual impact, environmental sensitivity, structure, stability, and access for installation and maintenance. The next important part of the system is the storage tank, plant room, and heat pump. The thermal storage tank should ideally be located in the central and accessible position. It needs to be protected and insulated and easy to maintain. The heat pump should be placed near the plant room with adequate ventilation and sufficient space for operation and maintenance. The plant room will act as the main connection point for pumps, collectors, and sensors, valves, and monitoring equipment. At this stage, the final storage volume and heat pump are still to be confirmed. Once the main equipment is located, we need to connect the system to the bungalows. So the pipe routes should follow the terrain and existing access path as much as possible, while minimizing excavation and disturbance to the site. Each bungalow will need also proper connection points for heating and domestic hot water. Isolating valve and leak detection should also be considered for operation and maintenance. This slide summarizes the journey of this pilot. We have completed the site characterization, and we have also completed the field measurement, temperature, logging, U value, and also we have completed the building model, SketchUp transits geometry, and we have developed the building model using SketchUp, and we are currently in the system model phase. The next step is to obtain simulation output, heating demand, and solar contribution, storage performance, and heat pump. After that, we will move to procurement alignment. This means matching the simulation results with the real equipment available from supplier. Thank you very much for your listening.